Hello, my name is Isagani Hernandez, and this is the final presentation submission for the final project of ADTA 5550. In this project, we are going to tackle data complexity challenges, improving CNN performance on complex data sets, and doing a comparative analysis of the MNIST versus the CIFAR 10 dataset. Project goals and scope. This project aims to analyze data complexity effects on model performance, applying architectural improvements to a low-performing CNN, utilizing TensorFlow low-level session graph architecture, and comparing a two-layer and three-layer convolutional and pool CNN design. For part two of the assignment, I am answering that the student should use, it is true that a student must use a TensorFlow framework directly in the coding. And for question two of part two, students must not use keras in coding. For part three, regarding the data set of images or audio files, the data set I chose was the Stanford Dogs dataset for fine-grained categorization. The dataset has a total of 20,580 images across 120 distinct breeds, with 150 images per class. This dataset is labeled with classes and bounding box annotations. I also have the citation in my paper. So the source can be found at visionstanford.edu. The dataset has four different files: images, a list of all files in the dataset, a training list, and a testing list. The image files have images of different breeds found in separate folders, and the annotation file has bounding box annotations for the images. The file list has a list of all files in the dataset and labels for all the test images in the dataset. These files are downloaded separately. For the training set, the images were split into 12,000 images, and the testing set was split into 8,580 images. The dataset meets the data requirements of the report because it is already organized and labeled, ready for deep learning. This dataset is suitable for deep learning because it uses fine-grained image categorization. And for the CIFAR 10 dataset on the report, for the downloading process, the CIFAR 10 batch files were downloaded from Canvas. They were then uploaded to Google Drive for access, where I could access them through Google Colab for my coding. The data was loaded, unpickled, normalized, and batched. I utilize CIFAR helper for the data preparation. And for the part four of the assignment, we have the baseline model architecture. The baseline model architecture uses two convolutional layers. Input data consists of RGB color images, has a shallow structure, has minimal capacity, and it is limited for the complex feature extraction. But we will go deeper into that further in the presentation. So here we have the input 32 by 32 by 3. We have the first convolutional layer, then it goes to a pooling layer, then it goes to the second convolutional layer, then it goes to the second pooling layer, and then it goes to the first fully connected layer, and lastly, it goes to the fully connected layer 2, which is the output. And for the test results, the model achieved 63.20% accuracy after 5,000 training steps. The accuracy quickly plateaued, showing a performance ceiling, and the simple two-layer CNN struggled with complex colored data. It seemed to have failed at performing at a high level. And now we are going to compare the ACC CNN MINTS dataset with the ACC CNN CFAR10 dataset. So the first dataset here is simple and it has a grayscale, while the CFAR10 dataset is complex using a RGB color scale. Going over the MNIST dataset, the model was trained at 5,000 steps. For the first step, the model performed at a 90.83% accuracy, and for its last step, it performed at a 98.75% accuracy. And for the CFAR10 dataset, at the step 100, it performed at a 43.60% accuracy, while on its last step at 5,000, it performed at a 63.20% accuracy. So comparing both data sets using the 50 data points, the MNIST dataset provided a higher accuracy level for each step from step 100 to step 5,000. The accuracy level remains at 98%, while the CFAR10 dataset depicts a significantly less accurate model from step 100 to step 5,000. It starts at a 43% accuracy and finishes at about a 63% accuracy. Although the CFAR dataset's accuracy improves by the last step, it performed significantly less accurate than the MNIST dataset. So here I analyzed that there was a 35.5% performance gap comparing both data sets. And I evaluated that the MNIST data set was simple, while the other data set was more complex. And for the explanation of the gap, one, the dimensionality and feature overload. The input size is larger for the CFAR10 dataset since it had a RGB scale and the MNIST dataset had a grayscale where overloading the shallow filters for the CFAR10 dataset. The second explanation is the semantic complexity. The CFAR10 requires complex semantic understanding to filter out background noise and focus on crucial details. So distinguishing similar animal classes is an example. And the third explanation is the architectural deficiency. The two-layer CNN lack the depth for the hierarchical layers to combine low-level color features into the abstract features necessary for a reliable object recognition. So overall, the CFAR10 dataset performed poorly because the model performed underfitting on the complex data that was given. Part 6 for the final project is the improvement strategy and implementation. So my proposal for this improvement of the model was to include another convolutional layer and making the model deeper. This will improve its training. It will also increase the model's depth and its ability to handle the more complex features for the dataset. By doing so, I would then need to update the fully connected layer 1 size and update the gradients in my code for the third convolutional layer. Lastly, I would increase the steps from 5,000 to 10,000. And for the improvement strategy and implementation, for regularization, I added a dropout to the fully connected layer 1, and this solves the overfitting and stabilizes the gradient flow, ensuring deeper capacity translates to better generalization. And then for the extended training, by increasing the steps from 5,000 to 10,000 steps, this allows the new larger network to fully converge and optimize its millions of parameters. For part 6 and part 7, the final results and the conclusion. The final test results are that the initial accuracy at 5,000 steps was at 63.20%, with the updated model's final accuracy at 10,000 steps performing at a 69.58% accuracy. Overall, the improvement achieved an increase in test accuracy. For the final results and the conclusion, capacity is key. The experiment proved that a model must be deep enough, and by adding the third convolutional layer, it matched the complexity of its input data, pushing performance past the initial ceiling. Regularization is essential because the successful improvement validates that increasing the capacity requires concurrent use of dropout and extended training to maintain stability and prevent destructive overfitting. And for the learn technique, this project provided essential hands-on experience in diagnosing model underperformance and applying complex architectural techniques in TensorFlow to achieve measurable improvement. And that is my summary. That is the final presentation. Now I'm going to go over the code for part 4. So the first step was to set up and import the necessary libraries. Here we have NumPy, TensorFlow, pathlib, import pickle. Here I printed out the version of TensorFlow that I'm using. And the next step would be defining the data paths. I imported the drive and I uploaded the batches from Google Drive. And then I loaded the data. I used the unpickle function, which loads and unpickles a serialized Python dictionary from a file. And after I loaded the data, I made sure to display the images. Here we have a frog. Here we have a truck. Here we have a car. The next step of the process was the pre-processing part of the data. Here I use a function for one-hot encoding. Here I use the class, the CFAR helper, which manages the data pre-processing, splitting, and batching. Then I use the function setup images, which pre-processes and stacks all image data for training and testing. And then I use another function called next batch, which returns the next sequential batch of training images and labels, which matches the explicit reshaped structure of the lecture document. Here is phase one for the convolutional neural network, and we are building the CNN. We are defining the supporting functions, which includes initializing the weights, where we initialize filter weights using truncated normal distribution. And then here we have initialize bias, which initializes bias with a constant value. So here we have the architecture of the model. We have the convolutional one, pooling one, convolutional two, pooling two, fully connected layer one, fully connected layer two, which is the output. The input image size is a 32 by 32 using 3 channels, the RGB. So here we have convolutional layer one with its filter shape printed. Here we have convolutional layer two. And then here we have the fully connected layer one. And then we have the fully connected layer two, which is the output layer. The next step was to do CNN model definition. I use the TF function. Here I use the convolutional neural network function, where we have layer one, convolutional layer, the ReLU, and then the max pool. Same thing for layer two. Then we perform flattening, and then we use that for fully connected layer one and the fully connected layer two. The next step was to calculate loss and set up the optimizer. So this function calculates the softmax cross entropy loss. And we utilize the optimizer add-on. Next, we trained and tested the CNN. We created a function for that called train step. This performs one step of back propagation and gradient descent. Next, I did test step, which calculates the classification accuracy on the full test set. Next, I did the training and testing loops. So I utilized it at 5,000 steps and created a loop. And I ran that code. Here you can see each step being printed out in increments of 100 from 100 to 5,000. and it lists the accuracy. So the first step here on step 100, the model was performing quite poorly at 43.60% accuracy, and it starts to get better as these steps keep furthering. And I can see it sort of plateaus around step 2000-ish, and it gets better again. And by step 5000, it performed at a 63.20% accuracy. And for the next Jupyter notebook, I utilize the same code. The only difference is I improved the model by adding another convolutional layer. This is the code where I added another convolutional layer. So instead of two convolutional layers, we have three convolutional layers in the new model. And I updated the code, initialized the weights. Here again, I added this for the third layer. And I also added a dropout layer. I did the same with calculate loss and set up the optimizer, train and test the CNN. Then we have the training and testing loops again. And here we have the results printed. And instead of 5,000 steps, this model will be performing at 10,000 steps. So here we have the step 100, where the model performed quite poorly at 38.59% accuracy, but it starts to improve as the steps increase. And as we keep going, we get to step 10,000, where the model performs at 69.58% accuracy. And that is the code for my final project. As you can see, this new model performs better than the previous model that had two convolutional neural networks. So adding the third convolutional layer increases the model's performance and accuracy, as well as including a dropout and increasing the steps from 5,000 to 10,000. In this video, I am going to now go over my project report to tie this whole presentation together. So in part 7, I had to do the project report. Here I have the introduction. This project explored the improvement of a convolutional neural network on the CFAR10 dataset. The CFAR10 dataset comprises images with an RGB scale. These images would be classified using a CNN with a TensorFlow AI framework. In this project, the CNN performance of the CFAR10 dataset was compared to the same CNN performance on the MSTIF dataset. So for in part four of this project, I focused on building, training, and testing the CFAR10 dataset. The CNN consisted of two convolutional and pooling layers. The diagram in part 4 can be referred to as the model's overall components in a deeper explanation. The model was built using a TensorFlow AI framework through Google Colab. The first step was to import the necessary libraries and define the paths. Following, the data was then loaded by batches, and for visual inspection, the images were displayed using indexing. After the data was loaded, the pre-processing began, and the CFAR helper function was utilized to manage the data pre-processing, splitting, and batching. After that, the CNN phase 1 begins. This includes defining the supporting functions. The functions included initializing the weights and initializing the bias. After the weights and biases were defined for each layer, the model was then defined using the TF function for the convolutional neural network function, where the model was then defined and the calculate loss and optimizer atom was utilized. Then we did the train step function and test step function. This part was important because it performs one step of backpropagation and gradient descent. Lastly, the training and testing loops were applied to calculate the accuracy of the model's predictions every 100 steps for 5,000 steps. And at 5,000 steps, the model performed at an accuracy level of 63.20%. In part 5, I compared the results of the 50 data points for the MNIST dataset previously worked on in homework 4 to the results of the 50 data points produced by the CNN working on the CFAR10 dataset. So the MNIST dataset performed really well compared to the CFAR10 dataset. At the final step of the MNIST dataset, the model performed at an accuracy level of 98.75%, while the CFAR10 model performed at an accuracy level of 63.20%. This part of the project highlighted the performance of both models and the effects of using them on different datasets. Comparing the model's accuracy led to a conversation about why the results differ and what is causing it. For in part 6, the premise of the section was to improve upon the model's performance on the CFAR10 dataset. I proposed a plan of improving the model's performance. The new model included a third convolutional neural network, a dropout layer, and increased steps from 5,000 to 10,000. These implications required updating the code for a new Jupyter notebook titled ADTA 5550 Final Project Part 6. This part of the project provided me with hands-on experience in improving a CNN model through different techniques. Using critical thinking and previous experience, I successfully applied my proposal and learned how to improve the deep learning model. In conclusion, for part 4, the model's performing at an accuracy level of 63.20% indicates that the model does not perform at a high level of accuracy. One can imply that utilizing 2 convolutional layers is not enough for this model to perform at a high level of accuracy for the CFAR10 dataset due to the dataset's complexity. For part 5, in conclusion, the MNIST model performed at a higher level of accuracy compared to the CFAR10 model. A conclusion can be drawn that the CFAR model performed poorly due to underfitting. Based on the understanding of both datasets, the CFAR model performed at its level of accuracy because the classification was applied to a dataset using RGB instead of a grayscale. The data was far more complex and required a model to perform more deeply. The images in the CFAR dataset also contain an abundance of noise, including background images and other objects, making it more complex for the model to perform its classification. By implementing another convolutional layer, a dropout layer, and increasing the steps to 10,000, the model could potentially perform at a greater level of accuracy. in which it performed at a 69.58% accuracy for the final step at 10,000. Um, in conclusion, by implementing the proposal previously stated for this section, the new model performed at a higher level of accuracy. As I just stated, it increased from 63.20% to 69.58% after the proposal was implemented. Implementing the changes to the model framework improved the model's ability to classify the images from the dataset. Although it was not a huge jump, I learned techniques to improve upon the model's performance. Perhaps future applications, I can try implementing a fourth convolutional layer and more steps to the process. Overall, this project taught me the fundamentals of building a CNN by comparing how the complexity of data sets affects the model's performance. I'll be well equipped with the knowledge of choosing the right model architecture for future projects. I learned the necessary techniques to improve upon a deep learning model's performance, specifically in part 6 of the final project. Lastly, this project helped me leverage my critical thinking skills and understanding of the topic through this hands-on experience. And that concludes my presentation.